Think about how a human child learns to recognize an animal. They see a small, fluffy creature, point excitedly, and guess, dog. A parent gently corrects them, saying, no, that's a cat. Over time, after seeing hundreds of cats and dogs, the child's brain naturally figures out the difference. For decades, computer scientists faced a massive hurdle. How do we teach a computer to do that exact same thing? The historical approach was something called rule-based AI. Programmers attempted to write incredibly strict, step-by-step logical instructions for every possible scenario a computer might encounter. That works for a game of chess, but it fails in the messy real world. Try writing a strict mathematical equation for a floppy ear, or programming a rigid set of rules that perfectly defines fluffiness. You can't. The modern solution to this problem is called supervised learning. Instead of giving the computer rigid rules, we give it a massive stack of flashcards. We feed it thousands of examples that have already been labeled with the correct answers. Take a look at this diagram. A label training dataset, in this case drawings of cats and dogs, flows into a neural network. By processing these examples, the machine learns to output an accurate prediction when handed a brand new image. Machine learning skips the impossible task of programming strict rules. It gives the computer the ability to independently derive its own patterns from pure experience. To truly understand how it actually learns from all of those experiences, we have to look deep inside the machine. These systems are built on artificial neural networks. Now, a digital neuron is not a complex biological cell. It is simply a tiny container that holds a number. That's it. When we show our network a picture of a dog, the computer sees a grid of pixels. It breaks the image down into numerical values representing brightness and color. Those numbers are then fed into the very first layer of neurons in our network. Look closely at this graphic. As numbers pass into the network's internal neurons, they are altered by parameters, specifically weights and biases. You can think of these as tiny mathematical dials that multiply and adjust the numbers as they travel deeper. Before the training process begins, every single one of those dials is set to a completely random position. So the very first time the network tries to classify an image of a dog, its guess will be wildly incorrect. That failure is entirely by design. A measurable, mathematically specific wrong guess is the required starting line for all machine learning. To fix that wrong guess, the machine needs an internal grading rubric. In machine learning, we call this a loss function. It is a mathematical way to measure exactly how far off the machine's prediction was from the truth. This diagram shows that exact cycle. The network makes a prediction. The loss function measures the gap between the predicted output and the true value, and that error measurement is sent right back to improve the model. When you add up all those individual errors across the entire data set of flashcards, you get what is called the cost function. It's the grand total of the machine's current ignorance. The machine reduces total error using a process called gradient descent. Imagine a blindfolded hiker feeling the slope, stepping steadily downhill to the valley's lowest point. With every step downhill, the machine's internal dials adjust the weights, making the next guess slightly better. There is a catch here. Basic multiplication and addition only allow a neural network to draw rigid, straight lines to separate its data. But a straight line cannot cleanly separate the complex, messy features of a real animal. Look at the graphs here. These functions are mathematical tools used to break up that rigid, straight line thinking. They allow the machine to represent more complex relationships by introducing curves and dens into the logic. Gradient descent finds the right direction, and these flexible curves provide the nuance. Together, they allow the machine to wire its own internal logic to match the squiggly, unpredictable shapes of reality. Even with all this elegant math, there is a constant danger in training an AI. If the parameters aren't tuned carefully, the machine will easily learn the wrong lesson entirely. Sometimes a model is too simplistic or lazy. It makes assumptions that are far too broad, like deciding that anything with 4 legs must be a dog. We call this underfitting. You can see the result in this chart. The decision boundary is a rigid, straight line that completely fails to capture the underlying pattern separating the stars from the triangles. On the other end of the spectrum, the machine tries too hard. It starts memorizing irrelevant background noise in the training data, like concluding a dog is only a dog if it's sitting on a green rug. This is overfitting. Notice how this chart demonstrates overfitting perfectly. The decision boundary contorts and waves frantically, drawing complex shapes just to perfectly box in every single piece of noisy, scattered data. The ultimate goal of an AI engineer is to guide the machine into the Goldilocks zone, a place where the model is flexible enough to capture the true underlying pattern, but resilient enough to ignore the noisy distractions. This beautifully relentless cycle, guessing, measuring the gap, and stepping steadily downhill, is the true engine of artificial intelligence. It's how a machine slowly wires itself to find the truth in a messy world.